Hello all, welcome to this video on distributed computing. Today I'll be talking about Lamport's mutual exclusion algorithm in distributed computing. This algorithm was suggested by Leslie B. Lamport, who is an American computer scientist and mathematician best known for his work in distributed systems. So he developed a distributed mutual exclusion algorithm as an illustration of his clock synchronization scheme. The algorithm is fair in the sense that a request for critical section are executed in the order of their timestamps and the time is determined by logical clocks. When a site processes a request for critical section, it updates its local clock and assigns the request a timestamp. The algorithm executes critical section requests in the increasing order of timestamp. Every site Si keeps a queue, which is a request queue of I, which contains mutual exclusion requests ordered by their timestamps. Note that this queue is different from the queue that contains the local requests for the critical section execution awaiting their turn. This algorithm requires communication channels to deliver messages in FIFO order. Since this is a mutual exclusion algorithm, it will have three sections. The first section is where the critical section is requested for. When a site Si wants to enter the critical section, it will broadcast a request in this format, which has a timestamp and its ID, message to all the other sites and place the request on the request queue, which is the request queue I. When a site Sj will receive the request message from site Si, it places the site Si's request on the request queue, which is request queue of J, and will return a timestamped reply to Si. The second section of the algorithm is executing the critical section. Now a site Si enters the critical section when the following two conditions hold. The first condition, L1, states that Si has received a message with timestamp larger than its own from all the other sites. And the second condition, L2, is its request is on top of its request queue, which is request queue of I. Now the third section of the algorithm is releasing the critical section. The site Si on exiting the critical section will remove its request from the top of its request queue and it will broadcast a time-stamped release message to all the other sites. When a site Sj will receive the release message from site Si, it removes Si's request from its request queue. Now, when a site removes a request from its request queue, its own request may come at the top of the queue, enabling it to enter the critical section. Clearly, when a site receives a request, reply, or release message, it updates its clock using the timestamp in the message. Now we'll see an example of how this is done. Suppose that we have three processes P1, P2 and P3. And suppose P3 wants to enter the critical section. Now what it does is, for requesting the critical section, it will send a request to both the processes P2 and P1. The request will contain its timestamp and the process ID. So that will be placed in the corresponding queues and will be updated accordingly. Now suppose that P1 also wishes to enter the critical section. What it will do is, it will send a request to both P2 and P3. So when P2 and P3 will receive request from P1, they will update their queues. So the second entry in the queue will be that of P1. Suppose that its timestamp is 2. Now the entries of the queue are in FIFO order. So that is why the second request is placed after the first one. Now suppose P3 has received a reply from both P2 and P1. We already saw that P1 had also requested for the critical section entry. Now before giving a reply to P3, what P1 does is it will check its queue. So on checking the queue, it will see that the request with the lowest timestamp is that of P3. So it will send a reply message to P3. P2 will also send a reply to P3. And after some time, P1 gets reply from P2 and P3. Now what is the case is, both P1 and P3 has received reply from all the other processes in the system. Now we already saw that to enter the critical section, there are two conditions to be satisfied. The first one is that the timestamp of the corresponding process should be on the top of the queue, and also it should have received reply from all the other processes. Now since both P1 and P3 satisfies the second condition, the first condition will decide who enters the critical section. Clearly, the timestamp of P3 is lesser, which is on top of the queue. So P3 will be entering the critical section. Now after exiting the critical section, P3 will send a release message to both P2 and P1. So accordingly, they'll update their queues and remove it. That is the request of P3. Now what happens is, we check the two conditions for entering the critical section. Now the only request left in the queue is that of P1. Now P1 will enter the critical section. After exiting the critical section, it will send a release message to both P2 and P3 and will update the queue accordingly. Now the queue is empty. No more requests are there for the critical section. Now we'll check the correctness of the algorithm. So the first theorem we are looking into is that Lamport's algorithm achieves mutual exclusion. Now this can be proved by contradiction. Now suppose the two sites Si and Sj are executing the critical section concurrently. Now for this to happen, we already saw that there are two conditions, L1 and L2. Now both these sites should hold it concurrently. Now this will imply that at some instant t, both Si and Sj will have their own requests on the top of their request queues, and that condition 1 will hold at them. Without the loss of generality, assume that Si's request will have a smaller timestamp than the request of Sj. Now from condition L1 and the FIFO property of the communication channels, it is clear that at instant t, the request of Si must be present in the request queue of J when Sj is executing the critical section. Now this will imply that Sj's on request is on top of the request queue of J. Now when a smaller timestamp request, that is Si's request, is present in the request queue already. Now that is a contradiction. This proves that Lamport's algorithm achieves mutual exclusion. Now the second theorem to prove is Lamport's algorithm is fair. Now this is again done by contradiction. A distributed mutual exclusion algorithm is fair if the requests for critical section are executed in the order of their timestamps. Suppose that a site Si's request has a smaller timestamp than the request of another site Sj, and Sj is able to execute the critical section before Si. Now for Sj to execute the critical section, it has to satisfy both conditions L1 and L2. This implies that at some instant in time, Sj has its own request at the top of the queue, and it has also received a message with a timestamp larger than the timestamp of its request from all the other sites. But what happens is the request queue at a site is ordered only by the timestamp, and according to our assumption, Si has a lower timestamp. So, Si's request must be placed ahead of Sj's request in the request queue of J. Now, this is again a contradiction. So, this proves that Lamport's algorithm is a fair mutual exclusion algorithm. Now, looking into the performance of the algorithm, for each critical section execution, Lamport's algorithm requires n-1 request messages, n-1 reply messages, and n-1 release messages. Thus, Lamport's algorithm requires 3n-1 messages per critical section invocation. The synchronization delay in this algorithm is T. Now we look at an optimization that is possible here. In Lamport's algorithm, the reply messages can be omitted in certain situations. For example, if the site Sj receives a request message from the site Si, after it has sent its own request message with a timestamp higher than that of Si's request, then Sj need not send a reply message to Si. Now, this is because when the site Si will receive Sj's request with a timestamp higher than its own, it can conclude that Sj does not have any smaller timestamp request which is still pending because communication channels preserve FIFO ordering. With this optimization, Lamport's algorithm will require between 3n-1 and 2n-1 messages per critical section execution. That's all for now. Thank you for watching.